Hey there, y'all. Today we're going to look at 2.2 on linearity and symmetry. In this section, your objective is that you'll be able to identify linear and nonlinear functions by examining equations of graphs, and then determine whether these graphs of functions have a line or point of symmetry. And so the two standards that we're looking at, FIF4, which we talked about yesterday, interpreting those key features of a function, and then FIF9 comes in talking about comparing the properties of two functions given in a different representation, such as algebraic, graphical, tabular, or verbal. All right, so let's talk about first, remind ourselves, what is a linear function? Remember that a linear function can be written in the form f of x is equal to mx plus b, or if we're not in function notation, we can write it with the y equals mx plus b, or any comparable forms where the slope and the y-intercept are real numbers. And so some examples of linear functions, like y equals 3/2 x minus 4, or 2x minus 5y is equal to 9, right? Those are examples of linear functions. We could also have, in Poincare form, y minus 4 equals 3x minus 1, right? We can have it in any form as long as I can manipulate it into slope-intercept form, and it would give me a line. Remember that also, just a reminder, that we could have y equals 7. Remember, that is a horizontal line. It would be a function. What are some non-examples of linear functions? What is not a linear function? Well, obviously when we talk back in Algebra 1, y equals to 2x squared plus 3x minus 4, right? Because that's not a linear function, that's a what? Makes that u, it's a quadratic, right? Or if I have y is equal to the square root of x, right? That's not a linear function, that's a square root function. If I have x is equal to 4, that's a line, right? But the problem is my line is vertical, meaning what happens? Does it pass the vertical line test? No, because the vertical line is a vertical line, so I have infinitely many points. It fails the vertical line test. Okay, so there's some non-examples of linear functions. All right, so let's look at these examples here, and I want you to first pause the video and look at these examples that we have here. We've got 3, and I want you to identify if it is a linear function or not. So pause here, take a chance, and look at it first. All right, I hope you paused, so let's look at these 3 examples and see why they are either a linear function or not. In the first one, we've got g of x is equal to 2x minus 5. Well, that is exactly in our form, f of x equals mx plus b, right? So this one is a function. It is a linear function. And we can identify what is the slope and the y-intercept of this linear function. The slope is 2, and the y-intercept is negative 5, right? When we look at b, x cubed plus 2, is this a linear function? No, because remember, linear functions are not going to have powers on the variables. And so this is not a linear function. And why is it not? Because it is a what type function? What power is it to? It's to the third power, so it is a cubic function. All right, example C, 3y minus 21x is equal to 12. Is this one linear? Well, we've got the x and the y separated out. There's no powers to either one, so it looks like it's probably linear, right? So can we solve it for y and get it into slope-intercept form? Let's do that. And so adding 21x to both sides, we get 3y is equal to 21x plus 12. And we can divide everything by the 3. And we get y is equal to 7x plus 4. So was I able to convert this into slope-intercept form? Yes. And so this is a linear function. And what is the slope? And what is the y-intercept? The slope here is 7, and the y-intercept is 4. So hopefully you got all 3 of those right, because again, it's not hard to identify a linear function when we're looking at the equation. We need to look at the powers, we need to look at the variables and understand that the variables cannot be multiplied together. We can't have powers on the variables. We can't have radicals dealing with the variables. to get it to that slope-intercept form. Okay, so let's move on to the next thing. So in example 2, we're looking at identifying linear functions from graphs. And in this problem, we say that Jen and Susie will work part-time in a smoothie store. The number of hours they worked increased for the first 6 weeks of the job. The graph models Jen's weekly earnings, and the table models Susie's weekly earnings for those 5 weeks. And we want to know if each is a linear function or not. And so when we look at a graph, and we'll deal with the table in a second, but when we look at a graph, we need to be able to take this and make all the points into a straight line. And so can I take a ruler and connect these 5 points and make a perfectly straight line along all of those points? The answer there is yes. Now, how could we tell if this might have gone off or not? Again, if I can't put a ruler and touch all those points at the same time with one ruler not moving, then it wouldn't be linear, right? So again, if I can touch them all with one ruler at the same time, linear. If any of them are off the line, one goes under the ruler or one goes above the ruler and it's not touching the ruler right on the edge, then it's not linear. We've got something else going on. And so let's look what happens with Susie in the table. To be able to tell in a table, we need to look at rate of change. Because between each step, our rate of change must be the same, because remember, rate of change is another way to express the slope of our line, right? So look at our changes in x. Plus 1, plus 1, plus 1, and plus 1. So my rate of changes are the same. But look what happens on the earnings on the y side. I've got plus 100, plus 100, plus 75, and plus 75. What happens between week 2 and week 3 and week 3 and week 4? Our earnings have changed. In the first 2 weeks, we were earning $100 a week, right? Increase on top of the previous weeks. But in comparisons of week 3 to week 4 and week 4 to week 5, it's only $75 increase per week. And so what that graph would look like, we'd have our first 2 points that would look like this. Well, we'd have our first 3 points. Those first 3 points would make a line this way. But then point 4 and point 5 would be like this. And so it's not going to make a straight line. Not all 5 points would hit that ruler and make one nice, pretty line. So this one, the top one is linear. The bottom one is not linear. And again, the reason it fails is that our rate of change is not the same for all of the points. Okay, so let's go on to the next example. So here we're going to look at line symmetry, and in the last example we're going to look at point symmetry. And here's the thing to think about line symmetry, is can I put a line on the coordinate plane? Now it could be a vertical line, could be a horizontal line, could be some diagonal line depending on the figure that we're dealing with, but can I put a line on the coordinate plane that will be able to reflect this? And so think about this, like if I draw a parabola, let's go back to Algebra 1 for a second. If I draw a parabola on the coordinate plane, like so, there it is. In this picture, we see that my vertex would be here, right? And I could reflect this across the y-axis because this point here and this point here are equidistant away from that y-axis, right? If my drawing is perfect, of course. And then same thing up here. This point and this point would be equidistant away. And I'd be able to reflect them across and the graph would be the same. Now, it doesn't always have to be the y-axis. We could be shifted off the y-axis. So if here's my coordinates and my graph is sitting over here. I could draw an axis of symmetry down that parabola. We talked about that in Algebra 1, how to find that line of symmetry. But I could still do the same, right? Here's my vertex sitting on the axis of symmetry, and this point are the same distance away, and would be able to reflect across into its opposite position. So, we look at the graph that we're given to the left here. Is this going to have a line of symmetry? Is there a place where I could put a line down the middle of this? And we're going to talk vertical in this one. And again, some other problems could be horizontal or different directions. But we're going to mainly look vertical at most of these because we're talking about functions. Is there a line I can draw that would let this reflect? And every point on the left side would reflect exactly to a point on the right side that's already there, and same with the right going to the left. Well, look at this. What shape does this kind of look like? It looks like a W, right? And so look at this point here, the x-intercept here. It's like negative 2.3. Go to the other side. I've got an x-intercept at positive 2.3, right? we look at this minimum down here. Down here at about -6, and the x-coordinate's just a little short of -2. I go to the other side, it's exactly the same point. I've got a maximum, a relative maximum here at my y-intercept of about 6. And so all of those points will be able to reflect across, in this case, the y-axis. The y-axis, which is the line x equals 0, because remember, whatever axis I cross, that's the line that we're talking about, and I cross at 0. That's my line of symmetry. Now again, could this graph be shifted somewhere else? Could I have this W sitting over here like this, and my axis, my line of symmetry be there? Yes. And we would figure out what value that is. It doesn't have to be the y-axis. It just has to be a line that I can draw through the graph that allows these points to reflect to the other side. This may give you a little bit of difficulty at the start, but you've got to use your mind and be able to think about, how can I flip this image? And remember, not all will flip. Some of them will not have a line of symmetry. Okay? And so now we're going to look at point symmetry. So with line symmetry, remember we talked about how I'm looking for a line where this will reflect across the left side to the right side. Point symmetry is a little different. Point symmetry is a rotational symmetry. And so, for example, can I take a figure like my binder here, right? And if I could rotate it 180 degrees about a point, would it still be symmetric? Now, obviously my binder's not, because it has the rings here, right? But if I were to open it up like this, right, and I have it like this, could I rotate it 180 degrees and it still look the same? Let's ignore the little tabby here, right? But if I rotate this 180 degrees all the way around, ignoring the little tabby part down here, would it still look the same when I rotate 180 degrees? Yes, because this side and this side are the same, right? And they end up in the same places. And so that's the whole key to point symmetry, is can I rotate it about a single point on the graph? Doesn't have to be the origin. It could be, but it doesn't have to be. But can I find a single point where I could take the entire picture, rotate it 180 degrees, and I still end up with the same thing? So let's look at this first picture here. We've got what looks to be a cubic root function on the coordinate plane. And again, we're looking for a point where it would naturally reflect around, or rotate around, not reflect. And so we see that this graph comes in like this, it starts to slant up and then goes out like that. So let's test this point right here, because I might be able to like helicopter this thing around, right? This cubic root function, and see what happens. Now, here's the best way to think about it. You've got to think about like having a whole new coordinate plane, and think about where things are at in terms of not the origin here, but pretend that where this purple is a temporary origin, right? And so I'm looking at how far like this point is away from the point that I've chosen. Well, in this case, it's up about 1 3/4, and it's to the right 5. Is there a point that corresponds in the opposite direction? So if I went up and right, I'd now be going down and left. And so from my potential point of rotation, I go down 1 about 3/4, and I go left 5, and I end up with a point in the same exact spot. I can find another one. Come out here. I'm up 2 and right 8. Can I find a point that is the opposite of that? Down 2 and left 8. Well, for my point of potential rotation, down 2, left 8 is right here. And so if I keep trying points, do we see that this is going to take this little cubic root function like this, right? And if I rotate it all the way around, it ends up in the same spots. And so my point of rotation is the red spot here, which is at what point on the actual coordinate plane? That point is 0, 2. And so this has point symmetry. And the point symmetry is at the point 0, 2. Okay? So let's look at the graph on the right. Can I do the same thing there? Again, especially with these graphs that we're dealing with point symmetry, you're going to look for a natural point where it might pivot around itself. And so where does that point happen? It looks like it happens here, right? So again, we're going to put a temporary coordinate plane here through that potential point. and look at points along the graph and see if they'll rotate around to the others. And so I've got this point here, which is 1 unit up and 1 unit right. And so I need to reverse both those directions. So instead of going up and right, I'm now going to go down and left. And so it was down 1, left 1, and I end up here. Let's look for a couple more. So if I come here, it looks like it goes through right here, right? So this is up. This is 6, 7, 8. That's up 8, right 2. Can I find one that is down 8 and left 2? So I'm at -1 originally, so I'm about to take me down to -9, and left 2, it's sitting there. I could test other points, but they're all going to do the same thing. They're all going to have a partner to pair up with, which means that that orange point is my point of symmetry. And so this has point symmetry through which point? Well, where's that point at? It's at 2, -1. So that's it for this lesson. Again, line and point symmetry can be confusing when you first look at it, but understand what you're looking for. Line symmetry. Can I find a place where I can reflect across a line left and right or up and down if we're able to reflect this way? And then point symmetry, can I rotate the picture 180 degrees and keep the same picture? And again, that point doesn't have to be the origin. So make sure you get your Google form filled out. Make sure you're taking your notes with this video, and I will catch y'all next time.